speaker of the day, and Erschler, she will speak about the isodiametric and isoperimetric function of groups.
Thank you. And first of all, I would like to thank Gulnara, Cornelia, and Alessandra. It's really a great conference. It's a pleasure and an honor to be here. And I will speak indeed about isoperimetric inequalities in groups, isodiametric function of groups, and something that wasn't mentioned in the title, but maybe I write now, so that would be mainly about isodiametric functions. Another invariant we will consider control function for the asymptotic dimension. These are two well-known natural invariants of a group. But today I will speak also about one new invariant that we introduced, and it turns out to be in strong relation with these two. So, and the new one, we call it elongations of snakes. We call them snakes, rather zigzags. Elongations of snakes in metric spaces, class for groups. And the results I'm presenting today is a joint work with Ivan Mitrofanov. Before explaining what are the notions that we study and what are the results, I want to make a general comment. The groups I'm speaking today would be mainly amenable groups, and you might ask, and what is relation with non-positive curvature? And but we will see today there are several reasons why the subject that we will discuss is very much related to the notion of curvature. Some invariants, in particular this one, this new one, could be considered as sort of deficiency to be hyperbolic. This is one reason. Another link with something with negative curvature would be not necessarily groups we will understand today, hopefully, but some questions we will discuss are very interesting to ask for limits of hyperbolic groups. We'll see several things in this spirit. And one other link with hyperbolic groups, again, about limits of hyperbolic group. Maybe at the end of the talk I will briefly speak about my joint work with Tiani Zheng about some of these invariants for lacunary hyperbolic groups. But first, let me explain the notions we discussed. So we have a finitely generated group G. First relevant notion is the Erschler function. Which measures, so if the group is amenable, then the Erschler function of n is the minimum of cardinality of the set, with where the minimum is taken over sets such that the size of the boundary of the set divided by cardinality of the set is smaller or equal than 1 over n. And another, yes, this is by the way, this is a very old notion. It was introduced by my former advisor, Anatoly Moiseyevich Erschler, in 1973, where he pointed out that it seems an interesting invariant of a group, and where he pointed out that in some examples, this function is larger than the growth function of group. So sort of implicitly, he indicated that there is a strong link between the growth function and the Erschler function, and asked for groups where it is larger. I will tell more on this in a moment. This is the Erschler function. And now we know many, many possible behaviors for the Erschler function. But for me today, even more important would not be the Erschler function, but the isodiametric function. To our knowledge, it was first isodiametric function. It was introduced by Piotr Novak, I think in 2007. Piotr used the notion isodiametric profile. We prefer to say function, not to have a confusion with the Erschler function, because for the Erschler function, also a very well-known terminology, isoperimetric profile, and it's inverse of the Erschler function rather than the function itself. And as a diametric function, it's not the inverse function. Let's call it as a diametric function. It considers again Erschler sets with the condition on the boundary, and it then minimizes not the cardinality but the diameter of omega with the same condition as the primary condition. There is an obvious link between isodiametric function and the Erschler function. If you have a set, its diameter is not less than inverse function of the growth of the set. Right? Cardinality of the set could not be bigger than growth function of this diameter, right? So obviously, this isodiam is smaller than v minus 1, where v is the growth function of the Erschler function. Erschler function of n. And the question, what are possible as a diametric function of groups? In the last years, we progressed a lot in understanding the Erschler function on groups. And the most general result is due to Brussels and Zheng. I will explain it a bit later. So basically, for Erschler function, any reasonable super exponential function is a Erschler function of some set, of some group. There is a very difficult and well-known question, and what happens for sub-exponential functions? In the conjecture of Grigorchuk, we don't have them unless polynomial growth, which happens as well known for polynomial growth groups. It's about Erschler function. But for isodiametric function, to our knowledge, until now, there were no examples apart of some classes of groups. For some classes of groups, one can check that the isodiametric function is actually inverse function of the Erschler function. And a question that Piotr asked many years ago, then he said a group. He didn't say a group. He rather said the Erschler function. I prefer to say, let's say that a group is lossless. If we have this condition. There are two versions of these definitions. Piotr rather took the growth function of the diametric function and said that it's equivalent to Erschler function. I write this slightly weaker condition for reasonable function. It's the same. You can plug in the growth function. For some very irregular function, it's not exactly the same. But let's say this is lossless condition. And so the question was, do we have any groups which are not lossless? And therefore, what are the isodiametric function? Can it be something else that is inverse function of the Fermi? And one of results I want to explain you today that actually there are many not lossless functions. So today I first would like to explain that for many groups are indeed lossless. So there was a reason to ask this question, but also that many groups are not lossless. This is one thing I want to discuss today, but then I want to discuss other properties of the isodiametric function. So both for Fermi function, for the isodiametric function, what we in general like to know, and what do these invariants tell us about our group? Can we know something else about the geometry of the group, looking on these functions? Can we maybe understand even some algebraic properties of the group if you know something about these functions? And what is the link between all these invariants? So this is something I would like to discuss. But first, before speaking about not lossless groups, let me already say what is the link, first of all, between isodiametric function and control function for asymptotic dimension. Again, another observation of Piotr, I think 2007 again, that the control functions, forgot what notation I like to use for control function, something with T, let's say. If we take some metric space of asymptotic dimension, of finite asymptotic dimensions, so some number m, one can speak about control function of the dimension, and well, here, let's say of and what can be said that control function is always greater than isodiametric function. Well, asymptotic construct. Actually, more generally, Piotr spoke not only about amenable groups, but about groups with property A, where he defined a generalization of Fermi function, a weak Fermi functions. This notion in case of amenable groups coincides with actual Fermi function. And so also for groups with property A, Piotr proved this inequality. And another question I want to discuss today, what are upper bound for the control function? There are some examples of control functions that we know before, mainly due to Brodsky, Didet, and Lang, for example, for Reef products, and but not much, as I said, was known about isodiametric functions. Another thing I want to explain you today, that many groups, for many groups, it would be asymptotic equivalence. Not only we would have a lower bound by asymptotic by isodiametric functions, but I will explain for many classes of groups there will be a matching upper bound. This would in particular hold, for example, for groups considered by Brodsky and Didet-Lang for Reef products, where not only one can estimate the control function, but where, after all, now with the one we evaluate the asymptotic of the isodiametric function, but also we will have many new examples of groups where, to our knowledge, we did not know control function of asymptotic dimension either, and now we can compute both isodiametric function, control function for asymptotic dimension, and a little bit later I explain this new invariant we are really interested in. Let us start maybe. When one writes here, one also sees everything. So let me first formulate our result about Reef products. So we have two groups, A and B, let's say finitely generated amenable groups. Just let me remind what happens with the Föllner function. This was this very old question that Erschler asked this time. He looked on Reef products and observed there is a very natural, straightforward candidate for Föllner sets in Reef products. If you have a group A, yes, I write A Reef product B. It's A that X and B are the lengths. Many people now use it vice versa, and sometimes I'm really criticized why I use this notation, but I was taught in my student years this way, and there is a serious reason, I think, to put the A on the left. There is some mathematical reason as well, but historically, I think a very important person for the notion of Reef products is Kaluzhnin, like in the classical theorem of Kaluzhnin and Krasner, and Kaluzhnin